So in section 2.2, we're going to be talking about characteristics of graphs and piecewise defined functions. First thing we want to look at are odd and even functions. So a function is odd if it's symmetric with respect to the origin. A function is even if it's symmetric with respect to the y-axis. Even functions are a little easier to tell. When you talk about this symmetry, about the y-axis kind of cuts it in half. It's, a mirror image on either side of the y-axis. The origin, not always so easy to tell because, you've got some in the first quadrant and some down here in the third quadrant. And you might be able to look and say, oh, okay, you can kind of tell that this one is flipped over from this side. But the way I sometimes look at it is, if I have a 0.11 over here, then the corresponding point are both opposite signs. Okay, so that's kind of, the way you can determine if something's odd. That's, one characteristic of a graph. Other topics are increasing and decreasing functions. So, when we talk about increasing, and let me put arrows here, and decreasing functions, we want to determine, as we look left to right, what's the graph doing. So as we look left to right, even though the arrow is pointing down, the graph is actually increasing. And it's increasing to here. And then it decreases to here, and then it increases again. Now, you're going to have to answer questions like, where is the graph increasing? Okay, where is the graph decreasing? Well, we look left to right, and then we use our x values to determine where things are increasing and where they are decreasing. So again, I'm going to put my arrows on here because we are assuming it's going on forever. But the arrow's going up, but as we go left to right, the graph is actually decreasing, okay? And it's decreasing from, we don't have a set point up here, so we say x, or we just say from negative infinity to x is negative 3, because it's decreasing from here to here. And the x value is roughly, and I'm estimating at negative 3. Don't use y values, only use x values to indicate increasing and decreasing. So this is decreasing. Now, and again, I'm going to write that here, decreasing. Right here is where it's increasing. And it's increasing from negative 3 to 0. So it's increasing from x is negative 3 to x is 0. And I forgot on the first one, but we can use interval notation. Okay. Sometimes with interval notation, it looks like points. I think I mentioned that before. So just, realize whether you're giving an interval or a point. So a lot of times it's helpful to identify your x's and then put it into interval notation. So from right here to here, we again are decreasing. And we are decreasing x is 0 to x is 2. And we use interval notation, 2 to 0. Excuse me, how about 0 to 2? Sorry about that. And we never use brackets when we have a continuous curve, because it cannot increase and decrease at the same spot. So we always use parentheses for our intervals. Then the last part, we are increasing here, and this is going again from x is 2 to infinity, or using our interval notation like that. Okay, so don't look at the way the arrows are pointing. If you're looking from left to right on a graph, decreasing, increasing, decreasing, and increasing. And always remember, this is something where students tend to mess up. They want to use y values. We use x values because typically your y values are going to be the same for many areas. Because, see, I'm increasing from here to here. Well, decreasing would be many of the same y values. So we always use x's. So we can, look at this example here, and again, look at more increasing decreasing, and constant. So this graph is weight as a function of age. So pretty much, at some point we go from weighing nothing to when we're like 25, we weigh 150 pounds. So if I wanted to look at increasing, it's x is 0 to x is 25. And again, we can use our interval notation. We're also increasing, looks like from 35 to 40. And we can use our interval notation there. Now we're decreasing from what looks like 40 to 50. These other two areas are constant. So we're constant from x is 25 to x is 35. Well, if I got room for that here, we'll find room. And from x is 50 to, let's say, 80, 85, whatever that is, or to, death, pretty much. So my weight scale would look like a heart monitor, up and down and up and down and up and down. So we're just going to just say 80 for all practical purposes here. But anyway, those are, more information you can get from a graph. Characteristics, we've got odd, even, symmetry type stuff. We've got increasing, decreasing. The next bit of information are what we call local maximum and minimum values of a function. And so the local maximum is the highest point on any interval for a graph. It occurs at some x, and then the minima or maxima is the actual y value. Okay, so the maximum is the highest point over intervals, the minimum is the lowest. So what we have here, we have a minimum here, and we have a minimum here. Okay, so we have a minimum at x equals -2 and x equals 3. So there's not an overall minimum, it's a local. So it's anytime the graph changes direction. So therefore this is not an interval, nor is this, because they're endpoints. They don't change directions. So those are my two, where they occur at, and the local minima are y equals -152 and y equals -27. So again, y is -152 and y is -27. Right here is a local maximum. So if you think about it, really, you're just identifying the points. At x equals 1, and the local maxima is y is 37. So when you're determining local minima, local maxima, you're looking at x's and y's. So it's just the wording sometimes that can trip you up. All right, here's another example. So at what numbers, if any, does f have a local maximum? Well, my local maximum is right there. So it's at x equals 1. And then what are the local maxima? Y is 2. Okay? I mean, don't overcomplicate this. Then we want to know about the local minimum. Okay, what numbers does the function have local minimum? So right here, and that is x is -1 and x is 3, because there are two locals. And what are the local minima? Well, y is 1 and y is 0. So these points go together. Okay, we can also pick up with more increasing and decreasing. So list the intervals on which f is decreasing. Well, it's decreasing from negative infinity to x is negative 1. Which in an interval looks like that. Well, that's increasing. Duh, hello. That's really going to screw you up. Sorry about that. Ignore that. That was decreasing. It's increasing from here to here. So x is negative 1 to x is positive 1. Which as an interval looks like this. And then it's increasing from x is 3 to infinity. Which looks like this. Now the decreasing, what we talked about earlier, negative infinity to x is negative 1. And it's also decreasing from here to here. So x is 1 to x is 3. Which as an interval looks like that. So try not to get confused with the difference between intervals and points, because it can be confusing. Okay. This next item is called the difference quotient. Not sure why it's here in this section, but it is. And so, we're given a function, and we're going to use this combination just to do some algebra evaluations. So, if I am going to evaluate this using here, so f of x plus h, my x plus h goes into here. Okay, so it's going to be f of x plus h minus f of x. So it's going to look something like this. I'm going to put my x plus h in for my x, and then I'm going to subtract my function value and put it all over h. So this is f of x plus h. This is minus f of x. And then I simplify. 5x, 5h, minus 2, minus 5x plus 2 over h. The 2's cancel. The 5x's cancel. I'm left with 5h over h. The h's cancel to give me 5. Okay, so it's kind of just substituting x plus h in for x, and then subtracting the function, simplifying things, and seeing what you're left over with. Just for time purposes, I don't want to keep you on here too long. I'm going to hold off on this one. Hopefully I remember to do it in class. One never knows about me, as you all have probably surmised already. And let's move on to piecewise defined functions. Piecewise defined functions, they're functions with 2 or more pieces. So I guess a good example of that is kind of what I have here with your phone bill. Now, back in the day, back in the olden days, 6 years ago, nobody texted as much as we do now. We called. So your phone bill, you would get so many minutes for free. So your bill would be, say, $39 for one line. If the minutes you use, which is your variable in a phone bill, is between 0 and 400. If you go over 400, then you get charged 20 cents a minute. So that's what this second piece is. But altogether, this is one phone bill, because if I put in an x value, I still only get one value for y. So if I want to find c of 100, well, in this case, that's my x. I look up here. X is between 0 and 400. So the cost for 100 minutes for my phone bill is $39. Nothing to calculate. Same thing for the cost of 400. Even though this has a 400, this is for more than 400 minutes. So it's still $39. Now, if I go over my 400 minutes, then what I've got to do is I've got to use the other equation because now my x is bigger than 400. So it's 39 times 0.2 times 480. I do this every time, minus 400. So it's 0.39, or excuse me, 39. We can tell it's been a long day. Plus 0.2 times 80, which is going to give me $55. Okay. Let me make this a little clearer here. 39 plus 0.20 times 80. So therefore my phone bill would be $55 if I used 80 minutes above my 400. So that's evaluating. So when you evaluate a piecewise function, you are picking which equation to use, and sometimes and you'll see there are different types of equations like these based upon your x value. Now we can also graph piecewise functions. So here is what a graph may look like. I'm going to go ahead and shade this dot in here. You can see that we have one equation to use if x is bigger than 1, one equation to use if x is smaller than or equal to 1. But in order to include all the values, x bigger than 1, I still start when x is 1, but I leave it hollow to say that this is just greater than 1. It's shaded down here because this does include when x is 1. Okay, that's kind of a tricky concept that throws off, more than one person. So don't feel bad if you don't get it right now. Hopefully, if we do enough of these, you'll kind of start seeing the pattern. Okay. But we don't extend the lines because we are cutting them off at 1, which is what this tells us to do here. So let's look at an example. And we are assuming, we haven't really talked about domain and range of equations much, but we are assuming our domain is all real numbers, negative infinity to positive infinity, and we're going to graph the piecewise function, and then from the graph we're going to determine the range. Okay, so here's your piecewise function. I have x plus 1 if x is less than 1, and then I have x minus 1 if x is 1 or bigger. Now, even though I'm going to graph this equation here, if x is less than 1, I still need to choose x as 1 as a starting point. So in my xy table, I'm going to choose 1 and then a number smaller than 1, which is 0. So I find f of 1, which is 2. I find f of 0, which is 1. Okay. Now, this point right here, since we are not including 1, is going to be hollow. That's the only one we need to worry about. Everything else is shaded. So if I go to over 1 up 2, I make this hollow, and then I go to 0, 1, and always make sure, since my x's I'm using are less than 1, I draw it in this direction here. So you see, this is where x is 1 here. Okay, so this is where we, are cutting things off at. Now to graph x minus 1, if x is greater than or equal to 1, I'm still choosing in my xy table 1 and then a number bigger than 1. Don't choose the same x's in both tables, then you're not going to have a function. All right, so when x is 1, I do f of 1 is 1 minus 1. I get 0, and we know that this one is going to be shaded. And then f of 2 is 2 minus 1, which is 1. So I go to 1, 0, which is here. Then I go over 2, up 1, which is here. And I draw my line going the bigger than 1 direction. So that's kind of how you're doing these piecewise functions. They are parts of lines. You've got to choose your x's based upon this right here. because this is the equation you use if my x's I am choosing are less than 1. Now, to find the range is my set of y values. So as we've done before, we look low to high, and in this case, we're going from negative infinity, okay, and we go to positive infinity. There is no breaks in the graph here. They overlap, so therefore, even though they're not connected, all y's are accounted for. So therefore, my range is going to be negative infinity to positive infinity. Okay, so that's 2.2. We will be doing more practice on these, and we will see you soon.